Okay, everybody, moving on through gas laws. All right, we finished Boyle's, Charles, Gay-Lussac's, and the combined gas law. Now, all of those laws have varying variables that are changing. However, in those four, the Boyles, the Charles, the Gay-Lussac's, and the combined gas law, we are keeping the amount of gas constant, right? So you're thinking about having enclosed gas in a container, and we're just basically playing around with the gas and playing around with its conditions. However, what if the number of gas molecules or moles of gas was to also change? So that introduces a fourth variable, and that introduces the other law. Okay, and the other law we're going to be learning is something called the ideal gas law. Okay, and the ideal gas law is as follows: the pressure times the volume is now going to equal the number of moles, which is going to be N, times R times T. And again, we'll get into this N and R thing in a minute. So pressure, volume, and temperature is still there. It's just this N and R idea. So how does this really work? And this is my perfect ideal cheeseburger if you want to know. Okay, so our pressure is going to now, what we're going to have to worry about with this law, and it looks easy, and it is an easy calculations. However, the units are really super important. In fact, you have to be in the right units. So you must follow the units. Okay, so again, units are really going to be important here. Okay, the units are going to be huge. So if you're not in the correct units, this is where you're going to have problems calculating. All right, so your pressure has to be in ATM or kPa. Right now, if you're not in ATM or kPa, you got to get in ATM or kPa. Okay, number two, the volume has to be in liters. Okay, if you're not in liters, you got to get into liters. So you're going to have to change milliliters to liters and so on. Okay, now N is going to be the number of moles of gas. Again, if you're not moles, you have to get from grams to moles, dividing by the GFM. Okay, and again, if you got to go from moles to gram, you got to multiply the GFM. Just a little note here. Okay, now R is represented by is called a universal gas constant. Okay, and that number is a number that helps to relate all of the variables together: the temperature, the number of moles, the pressure, and the volume. Okay, so that's constant for all gases. Okay, so that allows you to proportion these numbers. Okay, now there's two numbers to this. It's either going to be 0.0821 or it's going to be 8.31, depending on the pressure units. And again, we're going to see this in a minute. But again, R is a constant number. It's always going to be one of these or the other. Okay, and again, like we've seen before in the other law, the temperatures must be in Kelvin. If you're not in Kelvin, you got to get in Kelvin. So again, to repeat, you have to make sure you're in these units. If you're not in these units, you have to get in these units before you use the law. All right, and there are questions where you'll have to, go and convert before you get in. Okay, now correct units again, really important. Okay, the ideal gas law is different from the combined gas law, and that it takes to the amount of gas being considered, and when the amount of gas is changing, along with the pressure, volume, and temperature. So you're really keeping a lot of things in the air here. Okay, now air is a constant that mathematically relates all of these procedures together, or these values together. Okay, now here's a little bit more about R. R actually contains all of the units of the pressure, the volume, the moles, and the temperature. So you can see the unit for 0.0821, you're only going to use this number when the pressure is in ATM up here, right? So if you're given ATM, you have to match the correct version of R with the ATM. Now notice you also have a volume, the number of moles, and the temperature is also in here. So the volume, the temperature, and the pressure and the number of moles, the PVT, is all in here, in R. Okay? So this would be 0.0821 liter atmosphere per mole Kelvin. Crazy unit. All right, so again, you have to match it. Now, if you're in kPa, then you would match the kPa with this kPa and the pressure, you would use 8.3. So basically 8.31. So basically this is modified from ATM to kPa. The number changes when you use a different pressure value. All right, so not a big deal. You just have to make sure you choose that correct unit. All right. So next, if the now another good special thing you can do this is that if you know the grams of gas, right? If you know the grams of gas, all right, and you also can solve for the number of moles, then you would have grams per mole. And you know what grams per mole is? That is the gram formula mass. So just like in our boiling point and freezing point, you can actually calculate the gram formula mass of a gas using this, because you can, if you're given the amount of grams and you can solve for N with the volume, temperature, and pressure, and you know R, you can find the number of moles. Now, also, if you know the grams of gas, you can also solve for the volume and determine gas density, because again, mass divided by volume is equal to density. Well, if I know the mass and I can calculate the volume, then I can find the density. So there's a few little clever little things you can do. It's a clever little law. It really works pretty well. Again, it's not very hard. It's just you have to know which law to use, and that becomes sometimes the issue. So let's just practice a little bit and see where we are. All right, so let's just say you have this calculation, and it says how many moles of oxygen here. How many moles will occupy a volume of 2.5 liters at 1.2 atm at 1.2 atm at 25 Celsius. It's asking me how many moles of oxygen. I'm given some gas values, so I know I'm going to use the ideal gas law. I'm not going to use the combined gas law because the combined gas law doesn't have moles in it. This one does. All right, so I could rearrange this formula. I kind of sometimes like to do that. So if I divide both sides by RT, divide this by RT, I then can say that number of moles is equal to RT. Sorry, I can say that number of moles is equal to pressure times the volume over RT. So that's kind of easy, so I can figure this out. My pressure is 1.2 atm. All right. I'm going to multiply that by the volume, which is my 2.5 liters. All right. So I have that in there. My R, since I'm an ATM, I'm going to choose 0.0821 liter atmosphere per mole times Kelvin. All right. And I'm going to multiply that by my temperature. Now, be really careful. 25, you have to add 273 to get in the right units, which is 298 Kelvin. So I'm going to put my 298 Kelvin here. All right. And now what I find out is I'm going to go 8. All you dimensional analysis people will love this. And this is, again, equals to N. So this is ATM, cancels with ATM. Liters cancel with liters. Kelvin cancels with Kelvin. And now I have 1 over mole, which is moles. So we got this. All right, so if I do this and I calculate this, I'm going to get N equals 0.123 moles of gas. And that is my answer. All right, so really powerful stuff, because if I know the pressure, the temperature, and if I know the pressure, the temperature, and volume of any gas, I can calculate the number of particles. And again, once I have moles, I can go out to grams, I can go out to liters, I can go to number of particles, I can do whatever I want if I know the moles. Now, if they also gave you the grams in here, in the problem, I could take the grams divided by 1.23, and I would be able to get the GFM. All right, so that's another option you can do with this. So I'm just preparing you just in case. All right, so one more little sample. We'll do another one. It just says, what volume will 56 grams of nitrogen gas occupy? Well, they're giving us grams of gas, the amount of gas. So again, what am I going to use? I'm going to use PV equals nRT, right? So they want to know the volume that this is going to, 56 grams of nitrogen gas occupy at a pressure and a temperature. All right, so we're looking at volume. So what I'll do is I'll divide both sides by the pressure. Okay, and I'll get V equals nRT over P. Again, you don't have to follow this step if you don't want to. I just think it helps when you're doing this gas law. Now, I need the number of moles in order to do this, but I have 56 grams of nitrogen. So quickly, okay, I'm going to say 56 grams of N2. Be careful. Nitrogen gas is not N. It's got to be N2. Easily make a mistake. So you can divide this by 28, which is 14 times 2 for nitrogen. Okay, grams per mole, and I'm going to get 2 moles. Okay, so now I have my 2 moles. I have my R. I'm going to use 8.31 because I'm in kPa, so I have to use the 8.3 version of R. Okay, and I'm going to change this to 20 plus 273, which is 293, right, Kelvin. All right, so I have all my values that I need. So I'm going to take my number of moles, 2 moles. Okay, I'm going to multiply that by R, 8.31 liter atmosphere, liter kPa per mole K. All right. Again, I'm only putting the units in here to show you that they cancel. Okay, 293 K Okay, and that's all going to go over pressure, which is 96.0 kPa. All right, so moles cancels with mole. Kelvin cancels with Kelvin. And look at this, kPa cancels with kPa. And look at that, I'm left in liters, which is exactly what I'm looking for. So if I do this little calculation, I will end up with about volume is equal to 50.7 liters. 50.7 liters, which is correct. Let's just take a look. I'm going to take 2 moles times 8.31, times that by 293, and I'm going to divide that by 96. And I get 50.7. Yeah, so I just wanted to get that number down correct. All right, so that's it. All right, so we have 2 good answers. And the last little thing I want to show you just for fun, okay, is the fact of, let's just do something really simple. Let's take a sample of gas. Watch this. I'm going to take a sample of gas, PV equals nRT. All right, and let's just say I have the following conditions. Let's just say I am at STP, and I want to find the volume of any gas at STP. You probably already know this, but watch what I'm going to do. So I'm going to solve this for volume. I'm going to do the same thing. I'm going to say volume equals nRT over P, and I want to know it for 1 mole. So I'm going to take my 1 mole, I'm going to times it by 8.0821, okay, times my temperature of 273 Kelvin at standard temperature, right? And I'm going to put that over standard pressure of 1 atm, right? And let's just see what we calculate. If I calculate this, I'm going to get 1 times 0.0821 times that by 273 is the magic number 22.4 liters. Now, if you remember what is significant of that, you know that 1 mole of any gas at STP takes up 22.4 liters of an ideal gas. So now you have the actual calculation in real life of the conditions that produce 22.4 liters. Aren't you shocked that was actually kind of cool? Admit it. You know it's cool. And when you come to school, tell me it's cool. All right? So that's the little tidbit for today. Have a good day. We'll talk to you. Make sure you calculate everything. Watch your units, and you'll be good. Take care. Bye.